Okay, good. So welcome back, everyone. So before we talked about consortia, right? But imagine you have a consortium and then you have data together, then you need to model it, right? And you can use deep learning approaches, but the question is, are they interpretable? How do you do that, especially in chemical space? And that's what Moritz will tell us about. Moritz.
Yeah, thank you for the kind introduction, Andreas. Yeah, as you said, so the goal of the project I'm presenting here is to come up with a novel way to interpret neural network models. And the idea to do so is by looking at what kind of chemical knowledge is actually learned in the hidden layers of neural networks. Yeah, so if you think about a neural network, so you have here some input features here on the top, some chemical features, then you have hidden layers where some nonlinear transformations occur, and in the end you want to make some predictions. So I'm thinking of a typical QSAM model here where you could have classification or regression. And yeah, to do that successfully with a neural network, of course, here what's going on in the hidden layers, of course, the model needs to extract some chemical features that are meaningful to solve the task in the end. And the goal here really, our first goal here was to find what chemical features are learned in these hidden neurons of the neural network. Yeah, so if you think, for example, about the toxicity endpoint mutagenicity, you would expect that some neurons detect aromatic nitro compounds and others maybe polycyclic aromatic hydrocarbons. Because we know that these chemical features are associated with mutagenicity, and for the model to make accurate predictions, it somehow needs to detect these chemical features. And yeah, so the goal really was then to come up with some automatic workflow, how we can extract what kind of chemical features are learned in individual hidden neurons. Yeah, and for that, we wanted to combine information about training compounds that strongly activate a given neuron, and also weights that are learned by the network. In this case, weights that connect the input bits to a neuron. And the input here are, so as you can see, these atom environments, these belong to Martyn fingerprints from the RD kit. And yeah, what we then do is use something called formal concept analysis to systematically combine these two lines of information. So and these different formal concepts belong to combinations of compounds and bits that they have that naturally occur in the data set. And from these meaningful combinations, you can then go on and extract substructures. So these are parts of the training compounds that belong or are associated with these input bits that are considered meaningful by the network. Without going into too much detail here. So we have extracted the substructures, and then the next step of the methodology is how we can explain predictions made by the model with these substructures. So the first step here is to figure out how important a given hidden neuron is for an individual prediction. That we use a technique called integrated gradients. So here this, of course, simplified example. We have here 3 hidden neurons, and we get 3 different attributions. So these attribution values tell you how important each neuron is for an individual prediction, and yet they have a direction. So we have positive and negative attributions. Now the next step is to use these neuron attributions and map them onto the structures to get a model explanation. So first of all, we find, for the test compound, we look at what matches we found for substructures that were extracted for the given neuron. And then we share the attribution we found for the whole neuron between the atoms of the substructure. So if you look at these 3 neurons we have here, in the first case, we may have found, here this nitro group, a substructure attached to an aromatic carbon. So the total attribution of the neuron was plus 0.24. And yeah, we simply divide it here by the 4 atoms we have and get an atom attribution of 0.06. Yeah, in the same way we do it here with this aromatic amine structure. And in the third case, we just have this chlorine atom was in this case identified as a substructure. And yeah, in the end, to get the explanation, we just aggregate all the atom attributions. And yeah, this is shown here, indicated by colors. So red colors indicate positive atom attributions and blue colors negative. So positive, of course, indicating toxicity. And yeah, we do compare this method to a more established way of interpreting the neural networks, which is also based on integrated gradients, but applying it to the input features. Yeah. Okay, yeah, so what's the model we're actually analyzing, what data we're using for this? We've assembled a data set on Ames mutagenicity of around 8,000 compounds. And yeah, for this we combined several publicly available data sources. But we actually did not use the experimental Ames mutagenicity to label the data. And instead for that, we used the Deriving software from Lhasa, which implements a range of structural alerts for mutagenicity. Yeah, the advantage with that is that we're not dealing with any like experimental uncertainty. We have clearly defined rules as a ground truth, which we then can in the end compare to the explanations we obtain for the model. And yeah, so initially we want to start with a fairly simple model with just one hidden layer to, yeah, and as a proof of concept to see if it, our method somehow works for this still fairly simple model. And as input, we use Martyn fingerprints. And yeah, as you can see, yeah, the model performs fairly well on a test set. So, which shows us that it's not too challenging to predict these rules implemented in a direct system. So we have a high accuracy here. So how do we evaluate the model explanations? So as I've seen before, we in the end up with atom attributions. So it's like a continuous number that tells us how important a given atom is for a prediction. And to evaluate how well this explanation matches the ground truth, we use something called attribution AUC. Yeah, it's the same as the normal WOC AUC score, you know, to evaluate classifiers. And of course, what we do is we have this ranked list of atom attributions, so which atom is the most important and so on. And then we can compare it to the ground truth, so which atoms are part of the structural alert and which are not. Of course, this is the same mathematically as using AUC scores for this area under the WOC curve for a normal classifier. And that way we get evaluation of how well the explanation is for an individual compound. We did one more thing, because if you look just at individual compounds or the distribution we get for that, the evaluation will be biased towards structural features that are more common in the data set. So what we also did is for each alert that is implemented in Deriving, we get the average AUC score for compounds that match that, and then look at the average scores we get for different alerts to have a bit more of a more balanced evaluation. So here showing then some of the results. So we're comparing a new method, applying integrated gradients on the hidden neurons to applying it to the input features. And this is now looking at individual compounds. So here this left plot just shows all the individual AUC scores ranked for both methods. And here we have the associated median AUC. So what we actually can see is that both methods have very good, generate very good explanations for the majority of compounds. And yeah, the majority of compounds in both cases achieves an AUC of at least 0.8, which in our experience seems to correspond to fairly good explanations. But what we also see, if you look at the scatter plot, it shows the individual AUC scores for compounds. We see that both methods seem to perform better on certain set of the compounds. Now the second metric to evaluate with the average alert performances. Here it's, while integrate gradients and input was better on performing on individual compounds, it seemed. Here, they perform very similar. I would claim that my method is really superior. It's probably not statistically significant. But if you look at this here, then again seems that for certain alerts, either method performs better. And in this way, you could consider them as complementarily useful. None of them is clearly superior. Just looking at a few individual compounds now as well. So first here an aromatic nitro compound. So this is the Deriving alert. And here the different atom attributions we get with the two methods. So here IG input actually gives a perfect AUC score of 1, which means that all atoms that belong to the alert have a higher attribution than all the other atoms. The attribution for IG hidden look a bit different here. Pretty much the whole aromatic system gets highlighted. Which does not perfectly agree with the alert, but we can agree that, to an aromatic nitro, it's not incorrect to highlight the aromatic system that belongs to it rather than just the aromatic carbon, even though this then leads to a lower AUC score. On the other hand, the second example here, isocyanate, here IG input also gives a perfect AUC score, but here IG hidden, this is a case where it fails to detect isocyanate group correctly. And sometimes this happened in the data set with infrequent alerts, and isocyanate was an alert that was not very frequent in the data set. So this is a situation where the method fails to come up with a good explanation. But then you also have examples where IG input doesn't provide the correct explanation. Like this structure here, this quinolone-free carboxylic acid. It just seems kind of random, but it's highlighted here, but doesn't really correspond to the alert. And whereas, with IG hidden, there are also highlights all over the compound, but really this strongest attribution were assigned to this core here, which was the reason for the positive label. So here we get a correct explanation in the end. And similar here with this hydroxylate anthrachinone. With IG hidden, we get a more accurate explanation that highlights the whole core here. Which was not the case with IG input. So we also can actually explain negative predictions. So this was actually taken from a model that was trained on experimental Ames labels, and this is a negative Ames negative compound. We still have positive attribution for the nitro group, but then here especially these three fluorine atoms attached to the methyl group, they decrease electronic density and essentially deactivate the nitro group from being mutagenic, and this can be correctly indicated actually with both methods here. Then one more thing we looked at, so to extend our work from just looking at a neural network with one hidden layer to a deep neural network, which at least has 2 hidden layers. And here we first applied the method, or my method, to the first hidden layer to see if it still gives good explanations. And the scores we get here are very comparable to what we've seen before. That on individual compounds, IG input may have a higher median AUC, but if you look at alerts, they are very comparable, and it's different sets of compounds and alerts where each method outperforms the other. So this was just applying the method to the first hidden layer. The next step would be to trying to see, can we also do it for the second layer? But yeah, what we first wanted to explore is what's really going on in the second hidden layer. What do these neurons do? And yeah, we wanted to know, do they also detect specific chemical features? And to do that, we actually looked at, yeah, how well actually can neurons on their own classify the compounds as toxic. What I mean by classify here is we can consider the activation of a given neuron sort of as the prediction made by this neuron. And then again, we get a ranked list of compounds and can compare this to the label for the compounds, and then just see yeah, how well each compound, each neuron on their own could classify the compounds. And actually, if we look here in red at the neurons in the second hidden layer, yeah, most of them have either an AUC close to 1, which means that all the toxic compounds have a higher activation than the non-toxic ones, or an AUC close to 0, which means the opposite. So that non-toxic compounds have a stronger activation, but it's still, of course, discriminating between the two classes pretty much perfectly. But yeah, this was the case for neurons in the second layer, that they detect either all toxic or not or non-toxic compounds, as opposed to neurons in the first layer where we don't have these extreme like AUC scores. So if a neuron has like an AUC score of 0.7, it means that some of the toxic compounds have a strong activation, but not all of them. This corresponds to specific chemical features activating them. And yeah, for that reason, we then decided that we cannot apply our method to the second layer, or it's not very sensible, because the assumption really was that we would yeah, extract specific chemical features from individual neuron. But nonetheless, as I've shown on the previous slide, for this model, we can apply the method to the first layer and yeah, get good explanations. And it's really that what's going on here is that it seems that in the second layer, nothing novel really is detected, and just what was discovered in the first hidden layer is combined now. So all chemical features associated with toxicity are combined to be detected by the same neurons. Right, to conclude, we've developed a method to visualize what chemical features are learned in hidden layers of neural networks. And we have developed a method how we can use these discovered fragments on how to explain the neural network, so predictions that are made by the model. Yeah, in a few cases, we've seen poor explanatory performances, and that is was mostly associated when we had very rare, yeah, like structural features, rare alerts in the training data set. So the model still may correctly predict them, and the other method we looked at explained them may got it right. But yeah, in this case, the workflow failed to extract these substructures. But then again, there are we've seen other compounds where my method was superior to the other method we've looked at. And this really comes down to benchmarking. So yeah, we need to do more benchmarking for these explanation methods to look at a wider range of data sets and compare all the methods that are out there now to figure out, well, if are there any superior methods, or are they all comparable and have just different strengths and weaknesses and different like chemical features or data sets. Yeah, then I'd like to thank my PhD supervisors, Val from Sheffield and Sam from Lhasa, and also Lhasa for funding my PhD. And yeah, I'm happy to answer your questions now. Thank you.
Excellent. Very good, Moritz. Exactly on time. And Nadav has a question, as I can see. Nadav, would you like to verbalize that?
Yeah, I was just at a certain point, I was unsure what the output of the neural network was, but I think I'm okay.
Yes, so the output is just a prediction for mutagenicity, or well, how I'll label the data if a compound matches these direct alerts. Yeah, so that's just what the model was trying to predict. But of course, you could imagine this being applied to any Q-cell data set. Yeah, I hope that answers the question.
Yeah, thanks. And when it comes to interpreting features, I'm probably most worried about biases in data. I still remember ages ago, we were analyzing a data set of compounds and we were trying to classify bitterness of compounds, whether they taste bitter. And the top feature for bitter compounds was sugar rings. So why is that? I mean, because natural products are quite often bitter and natural products are quite often glycosylated, right? So they have sugar decorations, but that is what if you just apply the method, that is what you get. So you have to be really careful, So how do you sample the space, right? In order to build your model, you want to have an unbiased, whatever that means, data set. I think in chemical space, bias and signal is difficult to distinguish, to be honest. But that can be really difficult, right? When you are trying to identify features that are responsible for given, let's say, activity or class membership.
Yeah, and now to add to that, of course, if there's bias in the data, it's quite likely that the model will pick that up. And then if you have an explanation model on top of that, then it may also pick it up. So it starts really with the data and then going to the model, and then just the explanation is on top of that, but cannot solve what went wrong earlier.
Yeah, that's right. But that is because we cannot really sample evenly in chemical space. We don't know underlying distributions. We don't know how we should sample. And that is really, it's difficult, I think. But let's have here's a question from the audience. Mohammed, do you have a microphone? Do you want to verbalize your question as well? Otherwise, I can read that. That's no problem as well. Really interesting area of research. Very hard work. Thank you for your contribution. The question is, my question, is there any implemented code that will be provided? Another question, but let's do the first one first. Will you provide the code? Will that be open?
Yeah, so we are working now on a publication, and along with that, there will be like a GitHub and code will be available.
No, that's excellent. And what is the difference between using something like XML, so general explainable artificial intelligence, with normal toxic prediction techniques and using this approach? So is there anything specific to your approach, basically?
Yeah, I have to say I'm not familiar with XML, so I cannot comment on that. But what's generally specific to this approach is, well, most approaches out there try to interpret the models by looking at the input features and assigning importance to them. And yeah, what's different in our work is that we try to make use of what is actually learned in the hidden layers. So not going that far away from the input to the output, but taking into account what's happening in between. But yeah, I mean, future needs to tell how successful this really can be, if it's superior or not. Yeah.
Great. Thanks a lot. Thanks for providing the code. Indeed, that's really good to make it reproducible and the whole field can move forward that way, right? That's very good. Excellent. I think there's no more questions. Thanks a lot for your contribution, Moritz. Much appreciated.
Thank you for inviting me.
Thanks. Let's then go to the next presentation. So now we will move from chemical space to biological, so in particular gene expression space. So next speaker will be Anika who will talk about deriving time-concordant event cascades from gene expression data in DILI. Anika.
Hello, everyone. Everything okay technically?
Yep.
Great. Okay. Yeah, as Andreas said, my name is Anika and I'm a PhD student in the Bender Group at the University of Cambridge. And the project I'd like to present today is on drug-induced liver injury, where we've been looking from a systematic time series angle what happens between the treatment and the adverse effect. This was also published earlier this year in PLOS Computational Biology, and what we've been looking into more specifically is which cellular events, say for example pathways or transcription factors, take place before DILI, because if this is the case, they might be important for the pathogenesis. So the larger framework this fits into are the adverse outcome pathways, so short AOPs, which aim at formalizing knowledge on toxicity mechanisms by identifying these relevant events. And these are on different levels, so they're usually multi-scale, and also try to link them to causal key event relationships. The idea generally is that if you know then the earlier molecular initiating events or key events, this can then be used as an early warning flag for the later adverse event. And to evaluate causality in this concept, there are the Bradford-Hill criteria, which have been adapted to AOPs. And this includes essentiality. So is the molecular initiating event or key event, for example, necessary for the later adverse event? This is something that can be tested, for example, with knockouts. Then the second criteria is biological plausibility. So does it fit with what we generally know about biology and these events? And the last point is empirical support, which is something where we think we can support this with the right data. And this includes time concordance. So does the molecular initiating event or key event, for example, take place before the adverse event? And we think we have the right data for this. So the main goal of this study was then to see, can we quantify time concordance for already known key event adverse event relationships, because these are often rather qualitative, so we don't know how much time passes, for example, between the key event adverse event and how often we see it before. And on top of that, we thought maybe we can also use this concept to prioritize potentially new mechanistically relevant events. So just to clarify what time concordance is, I've added this figure. So here, like for a potential later event, which in our case is adverse histopathology, there could be different scenarios on what events might take place beforehand, for example. So time concordant is everything where we see activation already before we see activation of the later event. So in this case, it would be A and B, and that is irrespective of how they develop afterwards. So this one is, for example, going down again, while this one's going up. And in contrast to that, time-dependent events are those which are correlated with the later event or with time, which here is A and C. And this is also what so far studies have rather focused on. So from a practical angle, time concordant events are those which are potentially causal because they're found before the injury, while time-dependent ones are potentially good biomarkers because they reflect the progression and can potentially help to monitor the severity of injury, for example. So as potential earlier events, we've been looking at pathway and transcription factor activation, which were inferred from the gene expression data. And the data was derived from the OpenTGGates database, which contains transcriptomics and histopathology data on 170 compounds across multiple doses. And what's been particularly important for this work is that for each compound dose combination, we have, well, for many of the compound dose combinations, we have 8 time points. Out of those, 4 are within the first 24 hours after single dosing, and 4 are from between 4 days and 4 weeks after daily repeat dosing. So they cover a relatively large time frame, and the gaps between the measurements are quite different from each other. So the way we then analyzed time concordance was quite simple. So first, we inferred potential events from the data to make this more interpretable and also align with the AOP concept. So from the gene expression data, we used GSVA, so gene sets in combination with gene sets to infer pathway and transcription factor activity, and using the tox scores from the previous Sutherland et al. Paper, we inferred the so when adverse histopathology is first observed. Then on a time series level, so for each compound dose combination across the 8 time points, we inferred when is each event first activated. And then because, of course, our confidence in the time series with 8 time points is not very high, we test for significant time concordance across the set of time series we have in OpenTGGates. This allows us to separate potential confounders, like effects which are specific to individual compounds, but not to the adverse effect. Yes, so this exactly means that we don't find the compound-specific effects, but rather what is overall across the time series linked to adverse effect. So using this approach, we found that known mechanisms in DILI are indeed time concordant, but this also applied to many other pathways and transcription factors, which is why we looked for additional properties which can be useful to prioritize and characterize these time concordant events. And these are shown as axes here. So for example, we found as most significantly enriched pathway before adverse histopathology, recycling of bile acids, decreased bile acid metabolism, and this is indeed characteristic for cholestasis, which is one form of DILI. It's also found to be the most specific one, and among those, it is the most frequent one. On the other end of this spectrum, we also found that the most frequently observed key pathways and transcription factors are known in DILI. So this includes these point to ATF4 stress pathway, which makes sense given its biological role. So this is involved in the adaptive stress response, which only leads to adverse effects if it's overwhelmed. So based on that, you would expect it to be very frequent, but not very specific. I also highlighted the two events with the highest log fold change observed before injury, and these point to changes in fatty acid beta oxidation. So these pathways are not the most frequent or specific, but if they change strongly. So this seems to be an additional useful metric on top of the time concordance itself. So overall, we're able to characterize the time concordance of events using these different metrics, and can also link this to different biological functions. And this was found to prioritize plausible and known events. So the advantage of this approach is, of course, that it's automatable. So this was purely based on the data without requiring information on which pathway transcription factor you're looking for. So you can check time concordance for any event you might be interested in, as long as it is inferable from the gene expression and gene expression and histopathology data. And for that reason, we also developed a Shiny app where you can explore time concordance interactively. So this we call DILI Cascades. It's accessible via the QR code here, or also the link. In the app, there are two main functions. So first, you can derive time concordance for any definition of adverse histopathology and background histopathology that you might be interested in. So in the paper, we combined multiple adverse findings, but you might be only interested in biliary hyperplasia, fibrosis, and maybe light inflammation is something that you would tolerate as background. So this can be defined based on what you're interested in, and it will generate the time concordance metrics that I've introduced, and also some more based on your definition. So this is then summarized as a table, which you can explore interactively, and there are also different plots to show how the metrics relate to each other and how a particular event is ranked, for example. So for example, if you hover over this plot, you would see that this point is ATF4. It's an upregulation of the transcription factor. And then you would also see what is the true positive rate and positive predictive value for that. Yes, and also you can set the axis of the plots to show different metrics that you might be interested in. And then the second function of the app is to get more information on a particular relationship you might be interested in. So here you have to define the potential preceding event and the potential later event. And then what you will get is an overview on all the time series in which each of the event was activated. And if both of them are found, it will show the temporal order in which they are found. So is the earlier one found before, after, or at the same time? Yes, so we thought that the app is quite useful to characterize the time concordance, but there might also be other sources of evidence which can contribute or like help to find mechanistic events which are interpretable and useful. So the first thing we looked into was whether time concordant events are also time dependent. So something that was introduced before here. And here we indeed found that there are events which are significantly time concordant and time dependent. So here, each of these quadrants would map to one of the example curves. And in particular, these events, which are time concordant and time dependent, would be interesting as potential mechanistic biomarkers. So they show changes before we see injury and then also reflect the progression. And here we find that this is, for example, true for pathways pointing to a reduced level of plasma lipoproteins, such as chylomicrons, which is already being explored as a biomarker in chronic liver diseases. So as next step, we then thought, of course, time concordance alone is not very strong evidence for causality. And as outlined in the Bradford-Hill criteria, it's the best case if you can combine different sources of evidence. And that's why we then focus on time concordant transcription factors, because we know a lot about the causal interactions for those. What we did to infer transcription factor activity was to look at the expression of the downstream genes. And then we thought maybe we can also look into the time concordance of the mode of activation. So do we see beforehand changes in the transcription factors expression? So before we see changes in transcription factor activity. So if this would be the case, such as for this transcription factor up here, where we see changes in expression from the first time point and only changes in activity at a later time point, this indicates that the transcription factor is induced, so that we see that we see higher activity because of higher expression potentially. While if we only see changes in activity but not in expression, this would rather indicate that the transcription factor is directly activated. And in our data set, we found that this is, for example, true for all the nuclear receptors, which have been found before adverse histopathology. We then included two additional types of causal interactions, which link different transcription factors preceding injury to each other. So these are transcription factor target gene interactions, which were also used to infer transcription factor activity in the first place, and also interactions between transcription factor on the protein level. So we then looked into interactions which are also supported by time concordance. So we here require the edge and direction of the edge sign and direction to match the time concordance, and this identified a few clusters. Out of those, some are known. So for example, this one is linked to hepatocyte nuclear factor 1A and 4A, which are generally linked to liver function. And for HNF4A, it was found that if you artificially increase the expression, it can reverse liver failure in rats, which strongly indicates that it's causal. In a similar way, liver X receptor is also quite known in liver function, but we also find transcription factors which are not known in DILI so far. So this includes these two transcription factors, MICE1 and MICE2. And here for both, we have quite detailed mechanistic hypotheses. So we know that they are activated before adverse histopathology, they're likely induced, and we have potential upstream regulators which link to that. And this is all from a data set which was generated in a hypothesis. I believe that time concordance is a useful way to identify mechanistic hypotheses from time series data. Of course, not everything that is time concordant is necessarily causal. However, everything that is causal is necessarily time concordant, so it is a necessary criteria. We demonstrate the utility of this concept using time-resolved transcriptomics and histopathology data from the open TGGATES database. But also, I'd like to highlight that this can, in theory, be applied to other types of data and other data on other timescales, as long as it's possible to define the time point of first activation. We show that time concordance can also be combined with other criteria to prioritize mechanistic events. In particular for transcription factors, we're able to use prior knowledge in combination with time concordance to prioritize, to identify how transcription factors are potentially regulated, so the mode of regulation and upstream regulators as well. And we also provide a Shiny app to allow users to explore the results based on the TG-Gates database interactively. So this can be accessed through the QR code here. And if you're interested in the paper, I've also tagged that. So last but not least, I'd like to acknowledge my supervisors, Andreas Bender and Amshek Khan, and Jordi Munoz Moredas at GSK, who are also funding my PhD, and also the Bender and Hahn groups. So yes, thanks everyone for listening, and happy to take any questions you might have.
Excellent, great, thanks a lot. Are there any questions from anyone? So let's see what's in the chat. Applause, very well deserved. But yeah, David, please.
Yeah, also from my side, a warm applause, though virtual. It was very nice work. Thank you very much. And this really adds to our knowledge. I have one question about the human relevance, because in the TGK study, which you described, the most rich data also from time series point of view, also histopathology is in the rat. There were in vitro data is very limited for humans. So I wonder whether you have seen similar things in the in vitro data, and or have you considered these transcription factors, whether they are conserved in human as well?
That's a very good point and would definitely be interesting. But I didn't look into that because for the in vitro data, you don't have enough time points to follow a similar approach. So I could have looked into, do they change at all? But I couldn't have commented on if it's time concordant. So I didn't do that.
Yeah, thank you very much. Nevertheless, it's very interesting work and potentially new directions. Yeah, thank you.
Thank you.
Yeah, that's right, because you can always generate customized data, right, for a problem. But here, I mean, if you do omics profiling, in some sense, you can use that for anything, right? And because otherwise, you have practically you have too many problems. You cannot tackle all of them, right? And I mean, that's one of the reasons why cell painting data gets heavily explored in pharma and other companies, right? Why gene expression data, in some sense, is generic, right? But then the question is, what do you do then? It's not enough to have that very high dimensional data. You need to do the next step as well. And that was the aim of this work, right? Anika, what did you find most difficult in this? I mean, dealing with the types of data, finding a signal. What was most difficult in your experience?
So I think like for this approach, like if it's like, what would you like to have in terms of data? Like ideally, more time points and more time series, of course. So like this approach, however, is I think like it fits quite well, like in the in between. So if I had more time points, I would rather model it continuously. But it's like, because I have these weird time gaps, I think like this is the best we can do, like just saying like, does something take place before or afterwards? But that's like, yeah, it's something difficult to do if you only have 8 time points, which is also for the adverse why we included this. It can be also at the same time, because we then cannot exclude like that it may have been just before. And if we had a few more time points, probably we could have been more stringent with that.
No. The resolution. The thing is just if you generate the data, right, it's a combinatorial problem. Yeah, you have different doses or concentrations and then different time points, and then you need multiple animals and so on and so on. Yeah, that's right. Is there? Oh,
yeah, I'm aware that 8 time points is already a lot.
Yeah, relatively speaking. Yeah, David, you want to follow up?
No, it's a comment I hope Anika share with my impression. Every time I give, because we also did people work with TGKs, every time we start with acknowledgement to the team, because this will involve 10 pharmaceutical sciences in Japan, plus organization of Japanese government. It took them 10 years to build a database, and they shared it. I think it's really valuable resource. And also coming back to this morning's talk by Barry and other colleagues, such kind of open infrastructures is fundamental, as you said, Andreas, to go one step further, to make the generic more specific. Yeah. Yeah,
I think also for this work, it's like, I'm aware that it's like limited in translating to other data sets because they rarely have this size and resolution. But it's also, they already put in the effort to generate this database. So we should really make the most of it and learn what we can learn from it.
Yeah, that's right. Okay, so any final question or comment for Anika? Let's see. There's nothing in the chat. Let's see if on YouTube, if there's anything. No, I think we answered everything. Great. Thanks a lot again, Anika. Much appreciated. Okay. So now we move into one particular endpoint, and that's one endpoint that's actually quite well understood compared to many others, and that is skin sensitization. So Martyn from Lhasa will present on that.
Thanks very much. Let me just share my screen.
Sure.
Does that work okay? Can you see everything and hear me okay?
Very good. Yeah, everything good. Thank you.
Perfect. So yeah, hi everyone. Nice to be with you today. As Andre said, I'm Martyn from Lhasa Limited, and I'm going to be focusing on the endpoint of skin sensitization, and really focusing in on one particular in silico toxicology tool in the form of the dermal sensitization thresholds. And I'll explain what they are and the work we've done recently in this area. It's been a privilege to be able to collaborate with RIFM, the Research Institute for Fragrance Materials, in this. So yeah, we're grateful to them for all their contributions and help with this project. So in terms of what I'm going to cover, I'll start with a bit of background. I appreciate there's quite a broad audience here today probably, so I'll try and introduce skin sensitization, some of our models, and what the dermal sensitization thresholds are. And then I'll move on to the work that we've done and finish up with some conclusions and summaries. So start with the background, and apologies to those who this is common knowledge, but for those that it isn't, skin sensitization is an allergic response when you get repeated exposure to a particular chemical, and it's quite a common problem really. According to this reference, about 20% of the population are thought to be allergic to at least one chemical, and the kind of allergens you might find commonly: nickel, fragrances, hair dye ingredients, and it's a toxicological endpoint that many industries need to be concerned about. And as Andrea said, it's actually has a relatively simple adverse outcome pathway and is a relatively well understood endpoint. So you've heard about AOPs quite a lot already this morning. Here's a representation of the AOP for skin sensitization. One of the earliest to be sort of elucidated by the OTD and quite easy to fit on one slide. So I guess it gets seen quite a lot. But the key electronegating event is covalent binding of the usually electrophilic allergen to proteins in the skin. In terms of how skin sensitization is assessed, historically that would have been using animal models. So typically guinea pig tests or the local lymph node assay in the mouse. And in some cases, there will be human exposure data as well in the form of patch tests, diagnostic testing, that sort of thing. But again, in line with lots that we've seen already today, there's been lots of drivers for people to move away from those animal models towards new approach methodologies. So yeah, lots of reasons for that. Ethical, financial, legal, scientific, social, as I've said there. So that's led to the development of lots of alternative assays for skin sensitization. And these are linked to different key events in the AOP, typically earlier on in the AOP. And they're described in the relevant OECD test guidelines. And the kind of list is growing. So each time I look, there seems to be another test added to one of those guidelines. So there's really a wealth of new approach methodologies available for this endpoint. I'm actually not going to be talking about the assays themselves. I'm going to be talking about some in silico models for predicting skin sensitization, in particular the models that we produce at Lhasa. So Derek is the name of the piece of software. You've heard it mentioned already actually in Moritz's talk earlier. He was talking about the alerts for mutagenicity. I'm going to be focusing on the same idea, the same methodology, the structural alerts we have for skin sensitization. I wanted to just briefly talk about how Derek works for those who aren't aware already. So we have a set of structural alerts for a number of endpoints, and I'm going to be focusing on those for skin sensitization. We also have some kind of machine learning components as well. There's a fragmentation model that makes negative predictions when you don't get any alerts. And there's a nearest neighbors model that helps to make potency predictions, as well as predicting, is it a sensitizer or not? How potent is that likely to be? As I said, I'm going to be focusing in on the structural alerts today. And it's not really, I must confess, it's not really kind of novel science in the sense that structural alerts have been around for a long time. We first published some structural alerts for skin sensitization in the mid-90s, some work with Unilever. So it predates actually some of the in chemico and in vitro approaches, which I think is interesting. But nonetheless, they're still proved useful and they're still being used today. And And very briefly, the way they work is they describe a toxicophore, so a class of chemicals with a common substructure, by combining a number of aspects: the available toxicity data, sort of mechanistic understanding of why those chemicals are thought to be toxic, and some chemical principles, so sort of organic chemistry principles you can extrapolate from the data to similar chemicals. So that's kind of how the structural layout works, very briefly. And I think one of the reasons that they are, even though they've been around for a while, they're still in use, is that you have the opportunity to continually improve the knowledge that is housed in those alerts through analysis of public data and also proprietary data. So one of the advantages of them is that people can, if people donate proprietary data, we can sort of generalize that knowledge in a way that we can hopefully learn from it and expose that in a way that doesn't give away the confidential aspects of those structures. So I think, yeah, from my perspective, that's one of the advantages to their use. So I'm going to be focusing on those alerts today. And as I said earlier, it's in the context of the dermal sensitization thresholds. So or DSTs, as I'll call them for now, for short. These are an example of a threshold of toxicological concern, the skin sensitization. So hopefully TTC is an idea that might be familiar to some people here or to many. The basic principle is it's a threshold, so we're talking about exposure. And if a chemical exposure is below the relevant threshold, then the endpoint is very unlikely. So in this case, sensitization is very unlikely. They're not, they haven't been developed originally by us. They've kind of been worked on by a number of people over the past 15 years or so, the DSTs. So the key players really, they were first described by Unilever and then Rifum in the US, and Kao in Japan have also sort of contributed to their creation and use. Here's a little timeline that sort of describes the development over the past 15 years or so. So I guess we're just we're coming quite late to the party, I guess, but hopefully adding something to what's already been done by a number of other companies. I thought it might be helpful to kind of say where are these being used and kind of what sectors. So as I said, they were originally published by Unilever in the sort of personal care products. The example given in the first paper was something like an ingredient like a color, which might be used in such a low level that you could use a TTC approach to say that sensitization would be very unlikely, particularly in like a rinse off product. And then they've then been applied in the fragrance world. And I guess more generally across cosmetic ingredients. So this is a quote from a fairly recent paper from Cosmetics Europe and collaborators on next generation risk assessment for cosmetics. And one important tier of that kind of those frameworks is an exposure-based weighting. And for the endpoint of sensitization, that's where the DSTs come in. And I was also interested earlier this year, it's not just kind of personal care and cosmetics, they're kind of more widely applicable or potentially more widely applicable. So in the pharmaceutical industry, for example, the LC consortium, who are interested in extractables and leachables safety assessment, published a framework paper earlier this year where they were positing that the DSTs could be useful for assessing leachables in topical pharmaceutical products. So hopefully they're sort of something of interest to many in the audience today. In terms of where they come from, how a DST is derived, like all TTCs, they're kind of a data-driven approach. So you're trying to make use of existing data for chemicals that have been tested to say something about how potent are they in general, and what can we extrapolate from that to a new chemical. And specifically for sensitization, they use a gamma distribution. So the original work by Bob Safford, they gathered together a data set of sensitization data from the local lymph node assay, which is a mouse assay, and they plotted the potency of all the experimental values from that assay. So that's what the histogram here shows. On the left-hand side, you've got the least potent chemicals. As you move towards the right, chemicals get more potent. And what they observed was that you could fit a gamma distribution, which is this black curve, that actually fit really well to the distribution of the data. So most of the chemicals sort of, well, I guess you can see the chemicals are skewed towards the less potent end. So you're more likely to have chemicals that are weak and moderate sensitizers compared to strong and extreme, although there are a few in this data set. The advantage of being able to fit a distribution to this data is you could then start pulling out percentiles from that distribution. And that's kind of the the general principle behind a TTC, if you pull out, for example, the 95th percentile, you can start making some probabilistic calculations to say, well, based on all chemicals that have been tested, it's very likely that the potency isn't going to be more severe than this value, this 95th percentile, for example. The other key thing that was needed for determining the DSTs was an idea of a chemical's reactivity. And again, for those who know skin sensitization or the endpoint, there's been a lot of work done sort of understanding chemically what are the mechanisms behind that covalent binding, the molecular initiating event I mentioned. So, for example, back in 2005, Nora Abdullah and co-workers published some reaction mechanistic domains. So these are kind of common reactions, or common mechanisms, I should say, that cause sensitization. So what that means is that a human expert who knows these, has this knowledge, can look at the data set, and this is what they did. And just by looking at the chemical structure, you can say, is it like to be reactive or non-reactive? So they'd split that data set into reactive and non-reactive. And for each set, they fit a separate gamma distribution and took the relevant percentile to get a threshold. So these are the thresholds that are in the public domain. If you've got a non-reactive chemical, your threshold is higher, 900 micrograms per centimeter squared. And if you've got a reactive chemical, you've got a lower threshold of 64. So what that means is if you're doing a risk assessment for a chemical which you are concerned about sensitization, you can then compare the exposure, or you can use these in the kind of exposure-led risk assessment. And if the exposure is below the DST, then you might be able to waive a need to do sort of further testing. The final piece of work that was done by Cow and Riffham was to say that with reactive chemicals, there are still going to be some cases when you've got a really potent sensitizer. So they developed some another set of rules, sort of human expert knowledge to filter out those really potent sensitizers. These are called the HPC rules, stands for high potency category. And by filtering out those chemicals, they were able to derive a third threshold for those chemicals that might be really potent sensitizers. So this is kind of where things were at before we started. You've got 3 thresholds in the literature. And the key thing is, if you've got a chemical that you want to apply a DST, you need to assign it into the correct reactivity category of non-reactive, reactive, or high potency category. So hopefully everyone is with me still. That's kind of the background over. I guess the question to ask is, why were we interested in updating the DSTs? And there were 2 reasons that we started this work. First is that we know there's more data available in the public domain than when the studies were first carried out. So because they're very data-driven TTCs, they're going to be reliant on the data that's behind them. So if we have more data, we should get more, hopefully more robust thresholds out as a result. So we were interested in seeing what would happen if we made a bigger data set. How would that affect these thresholds? And the second consideration is that the knowledge needed to classify a chemical into its reactivity can be encoded into in silico models. And that's where the structural alerts in Derek Nexus come in. We already have that kind of body of expert knowledge within our computer system. So we were interested in seeing, could we use an in silico model to help automate this classification step and hopefully make it easier for people to apply this approach? Which then begs the question, if we do those 2 things, what will the updated thresholds be? And will they still be robust and protective for human health? Because I guess those are the key things. If somebody's going to try and use this in a risk assessment, we need to have confidence that it's going to work and work well enough. So onto the actual work that we did together with RFM. I said on that last slide that the knowledge required to assign reactivity can be encoded into an in silico system. But having made that assumption, we needed to kind of test it. So what we did, we looked at the original data set that was done in the studies, which for each chemical had been assigned its reactivity class by a human expert. And we processed that through the in silico model to see how well they would compare. That was our first test. Pleasingly, they agreed a lot of the time. A human and the computer agreed 86% of the time for this data set. And we did a bit more digging, as well as just a kind of binary, is it a sensitizer or not? We had a look at the kind of mechanistic information. So those mechanistic domains I mentioned earlier. We looked at how often a human classification of those mechanisms would agree with the mechanistic information found in the structural alerts. And again, that hopefully you can see in that confusion matrix, there's quite a good level of agreement, both in terms of if a chemical's sensitizing or not, and if it is, what mechanism is likely to be behind it. A couple more checks we did. we checked how well, kind of on a statistical level, how well a human classifier and an in silico classifier could predict the experimental activity. Both showed quite similar performance, very high sensitivity for both of them, and reasonable specificity as well. And the final check we did was to say, kind of a thought experiment, if we'd have used the in silico model instead of a human, what would the thresholds have been? And pleasingly, they were very similar to the thresholds that were actually derived. So that gave us some confidence that using an in silico approach here was kind of a reasonable way to go. Okay, so with that kind of piece of work done, we moved on to building the bigger data set to hopefully provide more robust thresholds. And to do this, it was essentially an exercise in collecting together all of the publicly available data from this assay, the local lymph node assay. We sort of looked in all your usual places, and we traced each data point back to the original reference. And I should say that the reference is Deriving, that's our own in-house toxicity database, so that helped us to be able to locate this data. We also went to the scientific literature. And by tracing them back to the original studies, we were able to curate that data set. So you heard again this morning about the importance of sort of the data that underlies all your sort of models. I've definitely found that to be true in my time in my career. So we spent quite a lot of time actually just curating the data to try and make sure that we had a good quality data set from which to try and draw these thresholds out. So if we found a study where it looked like the protocol wasn't followed appropriately, or maybe a negative result where the maximum tested dose didn't seem appropriate, we would reject those and try and keep a good quality data set. So that was the biological curation we did. I said we did standardization there. By that, I mean standardizing the chemical structures. So if any involved in building sort of Q-cell models, you'll know that there's some sort of subtleties around chemistry, and we wanted to make sure that the chemicals were represented in a consistent way, and that chemicals were, the same chemical wasn't present more than once in the data set. So that was the final step. And it left us with a data set of over 1,150 chemicals. Each of those had a single potency value in the form of an EC3 value. And where we had kind of mixed activity, so chemicals that were both positive and negative, we took a conservative approach and assigned them to sensitizers. And where we had multiple potency estimates, we took a median value for the EC3 to try and give a central indicator of potency. So with the expanded data set in hand, we compared that to the original data set to see what changed. Key thing was it was quite a lot larger, over 3 times as big. There was actually a more balanced sort of prevalence of sensitizers to non-sensitizers in the data set. So it wasn't, we didn't set out to change the prevalence, but it's just kind of what an aspect of the data that we collected. So our data set was approximately balanced in terms of sensitizers and non-sensitizers. And we checked how well the in silico model, the structural alerts performed against this data set. And pleasingly, even though we kind of tripled the size of it, the performance hasn't reduced drastically. So that was good to see. The key observation obviously was around the distribution of the potency values in our expanded data set. So I've shown on this figure, you've got the distribution I showed you earlier at the top, the original data set, and our expanded data set at the bottom. And hopefully you can see that the gamma distribution hasn't changed drastically, even though the data set's got larger. So that's important. I think it gives confidence around the original data set, actually, that gamma distribution was a kind of representative picture of the wider chemical space. And it gives us a good place to go from in terms of deriving new thresholds. So before I come on to what the kind of final results and what the thresholds were, I just wanted to make a note about those highly potent sensitizers. So I mentioned in the introduction that the set of rules have been published to pick out high potency category chemicals. And each rule is kind of linked to one of those mechanistic domains. So you don't need to worry about the details here, but for any kind of familiar with sensitization, you'll probably recognize some of these mechanistic domains. And actually anyone from an organic chemistry background, you'll probably recognize things like Michael acceptor, shift base forms, SNAR. So these rules were published in the literature by Dave Roberts in Riffham. We had the opportunity now to kind of check how well these rules worked on our expanded data set and whether there were any updates needed. Unfortunately, Dave Roberts was part of collaboration with us, which was really good to have him on board. So most of the time, the rules worked well, but there were a few minor updates we could make. This was mainly around sort of unusual toxicophores which weren't present in the original database, we could then sort of tweak the existing rules to better perform for those new chemical structures that hadn't been seen before. And with the updated rule set, we then set about encoding that into Deriving Nexus, so that could be applied again automatically using an in silico approach. And we were able to do that in a way where we tried to be as faithful to the kind of how a human would look at those chemical structures, and it agreed with a human expert 92% of the time, and was able to pick out the majority of those experimentally potent sensitizers. The one caveat I should mention is around rule number 9. So if you see in the little table here, rule 9 is to cover structurally complex chemicals. So really this is a case where a human expert looks at a structure and says, I don't actually know whether that's going to be highly potent or not. There's complexity in that structure, which means I'm going to say it might be highly potent as kind of a worst case scenario. That proved quite tricky to encode into an in silico system because it's quite a subjective rule. So that was the one which we couldn't encode. And that was one area where there might be a difference between what a human said and what the computer model says. Okay, the other thing to say about the HPC rules is originally they were designed as kind of I've called it a belt and braces approach here. They were designed as a kind of an additional step to filter out those chemicals. So I've tried to show that pictorially here. So the first step in the process was to assign the reactivity using those domains I've already described. And as a second step, the HPC rules came in to kind of filter out anything that was going to be highly potent for which the reactive DST wouldn't be appropriate. So that's how it worked and how it was published. We saw a kind of opportunity to maybe tweak how this was done, and could we do it all in one step rather than having this two-step process? Could we do it all in one go up front and then assign a chemical as reactive or non-reactive or HPC in one go? So that's what we looked at doing. We looked at taking our expanded data set that I described. We looked at applying the knowledge that's found, the structural alerts found in the in silico model, and in one go assigning a chemical into its correct reactivity class, and then deriving updated thresholds from those 3 classifications. So what does that look like? Well, bringing it all together, this is a kind of figure that encapsulates the final kind of results. You can see we started with 1,150 odd chemicals. As I said, about half of those are sensitizers, so 556, I think it was from memory. Of those, a small number were classified as non-reactive, and that led to a non-reactive DST of 710 micrograms. Most of them were classed as reactive, leading to a reactive DST of 73, and then the remainder were classed as high potency category, leading to a HPC DST of 1. I'll talk about how these compare to the original thresholds in a minute, but just to say we did do a little bit of looking into a small number of cases where chemicals were more potent than the threshold, which is, you wouldn't expect. And there were kind of reasons behind that. I haven't probably got time to go into the details, but it was kind of split 50-50 for those small number of chemicals. Some of them were cases where the computer model didn't quite agree with what human expert had said, especially in areas of structural complexity, as I mentioned. But equally, for about half of those, there was actually, it looked like it was problems with the biological data itself rather than the classifier. So even though we'd spent a lot of time curating the data, there were still cases where maybe the potency seemed to be overestimated. The EC3 value was sort of extrapolated from the dose response data, for example, which could be leading to overestimations of potency. So there were kind of interesting things we could learn from that analysis. From a user point of view, and if I've lost you, this is a good time to come back because I appreciate there's some technicality in there, but from a user point of view, we're hoping this is relatively straightforward because really there's 2 questions you need to answer. If you've got a chemical that you're interested in and you want to apply this kind of threshold approach, you need to ask, does it fall into a high potency category? If it does, you apply that DST of 1 microgram per centimeter squared. If not, does it fire a normal skin sensitization alert? If it does, then it's reactive, and you should apply that DST of 73 micrograms per centimeter squared. Oops. And if not, it's non-reactive. You should apply the 710 micrograms per centimeter squared. So yeah, hopefully that's a relatively straightforward way of applying this in the real world. So to sum up, the key thing really was that the updated values were very similar to the previously published values. And I've tried to show that on this little bar chart here, even though we've increased the size of the data set. So in some cases up to twice as many chemicals. So that was really pleasing to see that the values hadn't changed very much and should hopefully give confidence in their use. The other thing we were keen to look at was how protective they were of human health. So would these thresholds be suitably low to be protective against sensitizers in the real world? And again, I haven't got time to go into the maths, but you can do the advantage of a distribution again is you can do some calculations to work out how likely it is that that will be protective. The original thresholds were very protective, 95% so or more. And we found similarly high values when we checked for the updated thresholds. That was good to see that we've updated the thresholds, but it's not kind of reduced their usefulness or protectiveness. So to conclude, we've shown that an in silico model can be used to classify reactivity and high potency category chemicals. We've put together a bigger data set containing twice as many sensitizers as before. This has enabled us to tweak some of those high potency category rules to be a bit more performant or to more sort of accurately reflect the bigger data set. And we've derived some updated thresholds from that data set, which remain robust and protective. Recently published this work in Regulatory Toxicology and Pharmacology. It's open access, and I think Andreas has kindly put a link on the agenda, so feel free to go read that if you'd like more information about the details. The knowledge itself is available in our software, and we're interested in kind of if there's ways to increase sort of confidence in this approach. So one idea was could we do some case studies to try and show what this looks like in real life. So if anyone's kind of got ideas for case studies or is interested in being involved in that, please do let us know. Finally, just want to say thank you very much to everyone who's involved. Lots of people both at Lhasa and at RIFM. So thanks to everyone for their contributions. And thank you too for your attention. And hopefully I've left time for a couple of questions if there are any.
Sure. Yeah, we're doing fine with respect to time. And there are two right now. Manolina, do you have a mic?
Yes, thank you. Thank you for your great presentation. I would like to ask one question about when we have one concern compound and we don't actually know if there is a trigger on sensitization. So according to the schedule you are presenting now, we should define if we have any reactivity or not. So if we don't know and we don't have any data on that, which is the level we concern, the most conservative of a reactivity or a non-reactivity level? Thank you.
That's okay. I think the key thing really is to look at the chemical structure. So the whole kind of idea of the approach here is that you can, by looking at the chemical structure and applying what we know about sensitizers, you can make that judgment. Is it like to be non-reactive or reactive or highly potent? So if you know what the chemical structure is, if it's a defined chemical structure, then I would recommend doing that. And I guess there's two ways. We've talked about an in silico approach here. You can do that by looking at the literature as well and just using your own human expert knowledge. I guess the challenge might be if the chemical structure is unknown. That's where this, I guess, one of the limitations of this kind of approach. It requires a defined structure. So if you've got a UCVB or a biological extract, it becomes more complicated. But hopefully that helps answer the question.
Yes. So this is the basis for everything. Thank you. Thank you very much.
And Peter has a comment regarding the applicability domain. Peter, do you want to say a question?
Sure. Thanks, Martyn. Really interesting. It was just on top. I just thought, when you're classifying a new compound, is there any notion of how similar the new compound is to the compounds that help you define the distributions to get the DST? And if it's very dissimilar, would you trust the DST less or this kind of thing? Thanks.
Yeah, that's a very good question. So I guess the short answer is no. Currently, we don't have any way of showing that similarity to the training. Well, it's not a training set, but to the data set, I guess, behind it. But yeah, in theory, you could quite easily do that. We know what the structures are. They're in the public domain. I guess the only thing we can say is that as far as we know, it's all of the publicly available data for this assay. And we can say something about what kind of chemicals have been tested. So there'll be it's just the chemical space will be a function of the things that people have been interested in testing. So there'll be a lot of fragrances in there, for example, but there'll also be pharmaceuticals. Yeah, there'll be all sorts in there, preservatives. So that might give some idea of where it's likely to be more or less applicable. But yeah, it's a good idea. It could be another way of giving a bit more a concrete idea of how similar is my particular chemical to the data set. So thank you.
Thanks, Martyn.
No, it's good to see that you went all the way basically from data to a usable product, right? Because it's basically, the question is always what's actionable, right? So where do you have a tool that can really support a decision? In the end, that's what matters, right? Of course, you can do research before, but at some stage you need to think about that translation, right? Well, that's basically what you've done here, right?
Yeah, and I guess this is, in terms of a bigger risk assessment, this is a very small piece of the puzzle. So this kind of hopefully will fit into a wider picture of people might, if they're looking at something, they might already have existing data, as we've seen, or they might be able to do a read across. But this, if those aren't available, this might be one way to go down that kind of path to getting to a final decision, as you said. Yeah.
That's right. Okay. Yeah, I cannot see any more questions. There's one comment by Mohammed. All models are wrong, but some are useful. Yeah, well, I agree with that. Some are not even useful, right? But hopefully some are. But I found quite interesting to learn is, I mean, the better your model performs, the better you understand the problem, right? But I mean, not only performs on a test set, but on all space you want to classify, right? So you're not overfitting. I mean, a model that really performs better, right? The closer you are to the truth, right? That's also what happens in model space. Yeah? So found that important as well. Very good. Okay, great. Excellent. Thanks a lot again, Martyn. Yeah?
Thank you.
Okay, and then we come to the final speaker of this session, Peter Wright, freshly returned from Singapore. So a bit jet lagged, I think, but very good you're here, Peter, as well. Yeah, let's talk about animal data. And the question is, do we actually need to test compounds in multiple species, right? Or a single species? Can we use historical animal data as well as virtual control groups, right? So Peter looked into animal data. Peter, do you want to share a screen?
Yes, just give me 1 second, please.
Sure.
Okay. Okay, does that work?
Yeah, you're not at the beginning of the presentation, but I can see the slides.
Is that better?
Yeah, that's the first slide. Sounds good. Okay.
Great. Yeah, so thanks, Andreas, for the introduction. Jet lag is not too bad going from east to west. It seems west to east was so much worse. Yes, thank you everyone who's attending today. I'm going to present some work on statistically analyzing preclinical interspecies concordance of toxicity using the eTOX database. As Andreas said, I'm Peter Wright, and I'm in a group of Andreas Bender at the University of Cambridge. This is just a quick overview of the presentation. And firstly, we wanted to give a brief background on the two species testing paradigm and how sometimes there are still undetected safety risks detected in human later on. And then just the potential utility of identifying findings that are concordant between two preclinical species in light of potential increased predictivity for human risk. I'll then talk briefly about likelihood ratios, which are a statistical method to quantify concordance of toxicity, so how predictive toxicity is between species. I'll then talk about a previous study, which there's only one previous study to analyze this, and in light of its limitations, then move on to talking about the study design in the present study. I'll then talk on one specific result, which is we focus on the concordance of target organ toxicities between animal species. And then I'll finally look into just discussing just the importance of choosing appropriate statistical metrics when trying to quantify things like concordance, because they can lead to quite different conclusions. And finally, some conclusions and limitations of the work. Firstly, it's some background of concordance. So as you know, within ICMH M3R2 guidelines for toxicity testing of small molecules, we are mandated to test in two mammalian species, one being the rodent and one the non-rodent. However, despite this two testing toxicity paradigm, there are still 11% of drug iteration can be associated with undetected clinical safety risks in phase 1 human trials. And this is from 2000 to 2010, so the number might have changed slightly, but there's still some undetected safety risks. However, a previous study in 2017 showed that if we find, if findings are concordant or toxic in, for example, a finding is toxic in both the rat and the dog, this leads to increased predictivity for human. So hopefully identifying concordant toxicities could lead to reduced attrition or reduced undetected safety risks in human. Briefly, I'm just going to talk about likelihood ratios, which are a statistical method of quantifying concordance. There are two likelihood ratios that quantify two sides of the coin. One being the predictivity of toxicity in one species for toxicity in another species, which is quantified using the likelihood ratio plus. And on the flip side, there's the likelihood ratio minus, which quantifies the predictivity of absence of toxicity in one species for absence in the other species. Both are important, as we want to avoid both false positives and false negatives. I'd like to talk about likelihood ratios in terms of if one species we call a predictor species has a likelihood ratio plus, a likelihood ratio plus of a certain value, this would mean seeing toxicity in that species increases the probability of seeing toxicity in another species. And for likelihood ratio minus, I want to talk about them in terms of seeing the absence of toxicity in one species decreases the likelihood or probability of seeing the same toxicity in another species. Now, likelihood ratios are a useful metric because they incorporate both sensitivity and specificity of the test. However, they can be difficult to interpret, as in contrast to most metrics of accuracy or predictivity, they don't range from 0 to 1. Instead, they range from 0 to infinity. I'll start with a case study. It's a hypothetical case study on the right-hand side to demonstrate how to interpret them. So essentially, a likelihood ratio of 1 indicates there's no predictivity of a finding in one species for another. However, likelihood ratio pluses greater than 1 indicate a greater degree of predictivity. In contrast, likelihood ratio minuses are kind of, if they're below 1, this indicates degrees of predictivity of absence for predicting absence. So likelihood ratio higher, greater than 1 is greater predictivity of presence predicting presence, and likelihood ratio minus below 1 indicates greater predictivity of absence predicting absence. I gave there's a little case study showing that if, for example, liver toxicity in dog has a prevalence of 10%, what a likelihood ratio plus, a test with a likelihood ratio plus of 10 on a likelihood ratio minus of 0.1, how that would change the probability of observing that toxicity after observing it in the test species. So for example, a likelihood ratio plus would increase the probability of observing liver toxicity in dog from 10% to 52.6%, so quite significant. And a likelihood ratio minus 0.1 would decrease the probability of observing liver toxicity for that compound in dog, given observation of absence in another species to 1.1%. I hope that's not too confusing. We can discuss them later at the end of the talk if that helps. I want to briefly touch on the only previous study to analyze the concordance of toxicities between preclinical animal species, which was conducted in 2015 by Bailey et al. And in general, their finding was the presence of toxicity in one species is sometimes predictive for the presence of toxicity in another species. And this was shown via a median LR plus of 11.9. As we remember, LR plus greater than 1 is indicating predictivity for presence, predicting presence. However, on the flip side, they demonstrated that the absence of toxicity in one species was almost never predictive for the absence of toxicity in another species. And this is demonstrated by their median LR minus of 0.87, which is quite close to 1. However, there were several methodological limitations of their study, which I wanted to touch on as they're important for the current work. Firstly, in their study, they didn't control for exposure differentials. So for example, they could compare rat liver toxicity and dog liver toxicity after very different compound exposures. So the difference in toxicity could be due to compound exposure differences and not more related to a species difference in biology or ADME properties. Such an effect has been shown in the study by Monticello in 2017, where they analyzed liver toxicity false positive signals between preclinical animal species and humans. And they found that when exposure differentials were greater than 5, most of the false positives resulted in those cases. So rodent liver toxicity predicting human liver toxicity. In general, most false positives occurred when the rodents had a far greater exposure, which generally occurs in preclinical toxicity testing. You test much higher exposures. And the same was seen for dog and monkey. Secondly, the authors didn't quantify the statistical significance of the results. So for example, we could consider likelihood ratios as measures of effect size, but it's also important to quantify statistical significance of the results too, just in case we don't obtain too many false positives just due to a lack of data. And finally, and importantly, the data set they used to derive their results was only from marketed drugs, so drugs that pass through clinical trials. So these will be, therefore the results will be less relevant to new candidate molecules going through preclinical toxicity testing, which might not have as optimized safety profiles. So there are 3 key limitations. So now I want to talk about the present study design given the previous study. The data set we used was the eTOX data set, which is a preclinical sharing project of repeat dose toxicity data from 13 partner companies, mainly large pharma companies. The data set I used contained 2,800 repeat dose toxicity studies in total across 6 different species, and generally tested over 880 compounds. Now, the actual toxicity signals that I was using in the present study are 28 histological findings that study toxicologists observed or didn't observe in those studies. And they designated these as either treatment-related or not treatment-related. So I'm going to be looking at the predictivity of treatment-related findings for treatment-related findings and the flip side. And importantly, the data set includes drugs that failed in clinical trials. So it could be more relevant, results could be more relevant for new candidate drugs, products testing new candidate drugs. How the experiment goes, so it's quite simple, and hopefully the schematic makes it very obvious. We essentially assign one preclinical species as the predictor species, that's on the left, and use, for example, a toxicity signal, pathology A, as a predictor for a pathology B in a different preclinical species, which is the predicted species. Now we do these across compounds and studies, that's why we have these 2 vectors. And a 1 here would indicate that the pathology was observed to be treatment-related, and a 0, it was observed to be not treatment-related. And we count the number of false positives and true positives, and then these can be used to quantify the likelihood ratios from the previous slide. Now, in this presentation, I'll only be talking about target organ toxicities, which we defined as if there was any histopathology deemed treatment-related in that target organ, we define it as target organ toxic. So we abstract from the 28 histological findings to just target organ toxicity level. I hope that makes sense. And we applied several constraints to what we compared, which studies we allowed to be compared. So as we see in the middle plot, we're comparing findings in different studies. But in contrast to Bailey et al., we made sure that compound exposure between the studies compared was at least within 1 log unit of the Cmax exposure. We also ensured that some study covariates like animal sex were identical between the studies compared, and we didn't use mixed groups, so just male animals, female animals. And finally, we made sure that the repeat dosing duration for which the findings were observed was similar. So we'd only compare findings or target toxicities between acute studies, and not between acute studies and chronic studies, for example. Finally, I just wanted to touch briefly on how we quantified statistical significance of the results, in addition to likelihood ratios, which is the effect size. This is a method called the normal information method. And essentially, from the 2 vectors in the previous slide, we quantify the normal information of those 2 vectors, so how much shared information there is. We then randomize the 2 vectors and recalculate the normal information, normalized mutual information, which is now a randomized version. Do that 1,000 times and compare the distributions. And we essentially just compare that. The result will be statistically significant if the real mutual information is greater than the 70th percentile of the random distribution. It's sort of similar to a p-value of threshold of 0.3. I just want to touch on that briefly. So here is the primary result of the study. Essentially, the presence or absence of target organ toxicity in one species is rarely predictive of the presence or absence in another species. And what's plotted on the left-hand side is the LR plus values for the results, and on the right-hand side, the LR minus values. The dot colors indicate which target organ toxicity we are analyzing, and the x-axis indicates the species pairs. So, for example, dog, arrow, rat means dog liver toxicity predicting rat liver toxicity. What's the LR plus and the LR minus? So yes, the LR plus medians across the results was 1.69. which indicates quite low predictivity of target toxicities between these species. And similarly, the LR- median was 0.87, which also indicates poor predictivity of the absence of target toxicity or target toxicity in another species. Although in general, we see that the LR+ indicates that the predictive presence is marginally more predictive than the predictive absence between two species. Okay, so I'm going to now pull out one of those specific data points and explain how the LR+'s work in practice. So this is the case study for rat liver toxicity predicting dog liver toxicity. Given the results, we see that the LR+ was 1.89 and the LR- was 0.75. Both of these can be interpreted as the presence or absence of liver toxicity in rat only alters the probability to a small and rarely important degree for dog liver toxicity. In the data set, dog liver toxicity had a prevalence of 28.2%, so you can take that as a baseline. Then given the observation of rat liver toxicity, which had an LR+ of 1.89, it would only increase the probability of observing dog liver toxicity to 42.6%. And the LR- of 0.75 means that given the observation of the absence of rat liver toxicity, this only decreases the probability of observing dog liver toxicity from 28.2% to 23%. Now, the results may be dataset dependent. So we also looked at an external dataset from AstraZeneca, which tested 75 candidate drugs in non-rodents and rodents before first in human clinical trials. And for this specific case study of rat liver toxicity to dog liver toxicity, we observed very similar LR+ and LR- values. So that in general, the predictivity of presence or absence of rat liver toxicity for dog liver toxicity was low. This is just a plot showing the external data set in general, all the results, so heart, lung, liver, kidney toxicity, predictivity between the species, between rodent and non-rodent. And just to summarize, the LR+ median was 2.3, and the LR- median was 0.75. So yes, in general, the presence or absence of target organ toxicity in one species was only marginally predictive of observing the same in another species, although presence was slightly more predictive than absence. And so this is coming up to the final slide. I just wanted to touch on a very important topic, which is how the choice of metric influences conclusions of interspecies concordance. So I'm going to use the external data set and the predictivity of heart toxicity between from rodent to non-rodent. Specifically, I'll look at the predictivity of seeing the absence of heart toxicity in rodent or predicting the absence of heart toxicity in non-rodent. So for this result, the LR- was 1.091, which actually indicates worse than random predictivity. However, if one used a statistical metric called, for example, it's widely used the predictive values, and in this case, the negative predictive value, we'd obtain a result of 0.957, which essentially indicates that the absence of heart toxicity in rodent is predictive of the absence of heart toxicity in non-rodent in 95.7% of cases. However, when using such metrics, we must remember that it is known that predictive values like the negative predictive value increase with the decreasing prevalence of the finding in the predictive species. For example, a negative predictive value of 1 is obtainable with a pseudo species which never displays cardiotoxicity. So the likelihood ratios are generally a better type of metric for quantifying concordance. Some conclusions. The main result was that the predictivity of the presence or absence of target organ toxicity in one species for the same observation in another species was generally low. And this is probably due to differences in biology and anatomy, as we try to control for exposure differentials, so we could focus on differences in biology being a source of differences in toxicity. However, the predictivity of presence was slightly higher than the predictivity of absence, and this is in agreement with the previous study of Bailey et al. Both results were corroborated using the external dataset from AstraZeneca, which tested 75 candidate drugs in rodents and non-rodents. And we must be careful to always consider concordance results in light of the metrics used, principally predictive values or likelihood ratios, as these can lead to very drastically different conclusions of how concordant toxicities are between species. Some limitations briefly. When using any data set, there's something called the compound selection bias, which tends to be unavoidable. For the eTOX data set, for example, compounds appearing highly toxic in initial acute rodent studies would be unlikely to advance to longer term studies or studies in non-rodent. So very highly toxic compounds may be not present in this data set because we wouldn't have the pairs of rat and dog studies to actually derive the results. So the compounds, this is the compound selection bias. We didn't control for some known study covariates which were documented in eTOX, for example, administration route. So a target on toxicity in rodent, observed in rodent after IV administration may have been compared to a dog target on toxicity observed after oral administration. And we did this as splitting the data set up even more would severely reduce the number of significant results, but this is definitely a caveat. We didn't control for some unknown study covariates, which were not documented in eTOX, such as animal age or dosing regimen, which could have influenced the results. And we didn't consider for differences in interspecies plasma protein binding. So we controlled for exposure margins by controlling for the Cmax. However, the percentage of drug that's actually pharmacologically active will be those not bound to plasma proteins such as albumin. So using a measure of exposure such as Cmax unbound would have been better, the best way to control for exposure differences. And finally, we relied upon statistical predictions of finding treatment relationships from a previous work. As in eTOX, the original study designation of if a histopathology was treatment related or not treatment related were generally scarcely reported. So we had to rely on some statistical predictions for this work. And finally, some acknowledgements. Thanks to Andreas for letting me present today and the wider Bender group. Hope you're all well. And I'd also like to thank my collaborators at AstraZeneca and Lhasa. And finally, the NC3Rs for funding my PhD. And if you have any questions or suggestions, please get in contact. Thanks.
Thanks, Peter. Thanks a lot. And I think one thing you didn't outline that extensively is that actually cleaning up the data, right? The terminology and so on. There was actually a good chunk of the work as well to actually prepare the analysis that you were performing, right?
Yeah, it's definitely about 50% of the PhD was data cleaning as opposed to just the analysis after.
Yeah. Okay. Are there any comments or questions from anyone? David.
Yeah, congratulations, Peter. It's very interesting work. I only have two very naive and probably question that is obvious. First, it's actually apparent the target makes the difference. Partially, you mentioned this already, the biology. I mean, one is ADME, the other is biology. So apparently the evolutionary distance of the targets would make a difference. That would be intuition. There, I want to hear your opinion on that. The second one is I probably did not get fully your methodology, but appears to me that if there is a strong imbalance, let's say, many cases the drugs showed both histopathology in both species, and in other cases it just show one, this would make what you describe a likely outcome. Namely, it's easy to predict based on one positive finding, another positive finding, but if it's negative finding, it does not really help to predict the absence of another.
Okay.
So these two aspects, yeah. Thank you.
First, the pharmacological, the primary target would make a difference, especially in terms of if the species was not, the species aren't pharmacologically similar. That could lead to differences in the toxicity, which we didn't account for. I would say that eTOX does have some annotations for the primary target of the compounds, and it could be sub-analyzed whether different species actually had these targets. That would definitely make a difference. And your second point about absence of toxicity or presence, it does seem that in most studies, we find that the predictivity of presence is higher than absence, which is slightly concerning given that if preclinical studies show absence of toxicity, even at higher exposures, this would go into human and perhaps show toxicity. So the predictivity of presence and absence are both equal, both very important and should be considered. So quantification of likelihood ratio of plus and minus would be required. But also on top of that, these differences in metrics. So it's so essential to understand what your metrics are doing If you have very low prevalence, it's very easy to have very high negative predictive values. And if you have very high prevalence, it's very easy to have high positive predictive values. But it might indicate actually any predictivity of your test. Whereas likelihood ratios, generally, they consider the prevalence as a baseline and only on top of that show the predictivity. So it's very important to look at both sides and choose appropriate metrics.
Yes, thank you for the explanation. And the side observation would be that it asks your observations lead us to ask a third natural question. Human is just the third species.
Yes, yeah. Hopefully identifying findings that are concordant between these preclinical species should lead to increased translatability to human, at least while we remain within the two species testing paradigm. If they're concordant between the species, should be more similar to the third species. Hopefully.
Yeah, I think the goal is shared by the whole community, but the fact that actually if you observe a lack of pathology in one species does not tell so much about the absence of toxicity in another species. I wonder how much is translated if you see lack of his pathology in two species and the third, which is human.
That can be, that sort of an ask can be done as well in using a decision tree sort of approach. If both absent, what's the predictivity? That's a good source of future work.
Okay, great. Thanks a lot. Is there any final question? Lily says, great work, valuable content. Thanks for presenting. Yeah, much appreciated. Is there any final comment or question from anyone? Okay, I'll just see if there's something on YouTube as well. And otherwise, yeah, no, there's nothing there. No, very good. Excellent. Let's thank all the speakers. Thanks a lot, Peter. And we will continue at 12:30 UK time in 20 minutes. See you in 20 minutes, everyone.